Good morning, students. We will start a discussion on the last ensemble in our course, which is the Grand Canonical Ensemble. So, this is the ensemble where the member systems are all specified by a macro state at constant chemical potential, volume and temperature. So, you can instead of volume you can take any other generalized variable such as magnetization, for example, for spins in a constant magnetic field. Let me also tell you that this is the most important ensemble in statistical mechanics, in the sense that it naturally provides for the correct enumeration of states for systems in quantum mechanics. So, you will realize in chapter 3 that the most natural ensemble to do calculations in quantum systems is the Grand Canonical Ensemble. So, I am going to spend the last part of my lecture precisely on this issue, on this ensemble, which is the ensemble at constant chemical potential, volume and temperature. So, the Grand Canonical Ensemble is maintained by fixing temperature, and I know I can fix temperature by allowing for energy interactions with the reservoir, and I can fix volume in any system by just having fixed walls. So, there is no work, mechanical work, so walls do not move and there is no mechanical work, and I can fix the chemical potential by allowing exchange of particles with the reservoir. So, this is called as thermal interaction with the reservoir, and this is called as exchange of particles with the reservoir. So, if you allow for energy interaction, it keeps temperature constant. If you allow for exchange of interactions, exchange of particles with the reservoir, you can keep the chemical potential constant, and if you keep fixed walls, do not allow them to move, then that would just fix your volume, thereby saying that there is no mechanical work done on the system. So, I can draw a schematic here to show what is going on by drawing my system and connecting it with a reservoir. Okay, so, you can say that the system is in constant volume because the walls are fixed. Okay. So, the walls are fixed, and you allow for interaction of energy. So, there is exchange of energy with the reservoir that keeps my temperature constant. Okay. And you also allow for particles to be exchanged because the walls can be made to be porous. So, that would keep my chemical potential constant. Okay. So, now let us look at a typical microstate that the system can rest in. So, a microstate here is basically specified by a label nu. I am going to use a label nu because mu is already reserved for chemical potential. So, a microstate here is nothing but the set of position and momentum coordinates, it belonging to a certain instant when the number of particles is n nu, because the number of particles are also changing. So, I here belongs to the one of the n nu particles in that particular nuth microstate. Okay. So, our microstate is not just Qi and Pi for a fixed n itself is varying from microstate to microstate. Okay. So, that is the definition of a microstate here, which tells me that the probability of finding my system in a microstate nu such that the number of particles are n nu, okay, is nothing but the Boltzmann factor e to the power minus beta into the energy scale, which in this problem is the Hamiltonian for the nuth microstate, where you have n nu particles minus an energy scale which is due to the constant chemical potential, which is mu times n nu. So, that is the energy scale for the problem. Okay. So, the energy scale for the problem is not the Hamiltonian alone, it is h nu the Hamiltonian for the nuth microstate minus the chemical work that you are allowing to be done on the system, and n here is the number of particle in the nuth microstate. Okay. Well, naturally this PDF is not normalized, you have to normalize it, and so the factor, the norm is the grand canonical partition function, and I am going to give it a different label with the double horizontal strikes. So, this is the partition function of the system in the grand canonical ensemble. Okay. So, let us call this as equation 1. Now, you can easily see what should be the expression for the partition function. So, the grand canonical partition function that provides the link with thermodynamics can be very easily obtained as simply summation over all microstates of this Boltzmann factor. Okay. So, let us do that. So, we will take summation over all the microstates. Now, microstates is the doublet of nu n nu, okay. That is a combination which specifies a single microstate, and I am going to sum over the Boltzmann factor, which is e raised to minus beta the energy scale okay. Now, this is a double summation. So, it is in some sense unrestricted sum. So, all possible values of n nu are taken, but I can convert this into a restricted sum and do this calculation easily. So, what I am going to say is that let me first compute the sum over all possible number of particles. Okay. So, that would be saying that I am going to take the summation over n nu. Okay. So, here the n nu will go from 0 to infinity, all possible number of particles. The extreme values of n nu would have a probability which is very small, as can be seen. Okay. So, once you have fixed your n nu, you can compute the inner sum over all microstate such that it takes the value n nu from the previous sum. Okay. And for each n nu that is set in the outer sum, you compute all possible microstates, and so I have to take e to the power beta outside, because that does not depend on the microstate nu. Okay. So, this will be acting only over e to the power beta mu n nu, because this is just the variable here is just the number of particles in the microstate, and the inner sum would now be on the microstates such that the number of particles is fixed to n nu by the outer sum summation over e raised to minus beta h nu. Is that okay? So, now it is like changing from unrestricted sum to restricted sum. So, this thing is a restricted sum. Okay. So, you for example, you in the outer sum n nu could be 50. So, you have 50 particles in your system. For these 50 particles, compute all possible microstates by arranging the particles in the box, and that is your inner sum. Then you change 50 to 51 and then compute all possible microstates for these 51 particles and compute the inner sum. So, this way you take the number of particles in the outer sum from 0 to infinity and compute the inner sum. Okay. Now, if you pay attention to this inner sum, it is looking very familiar. Okay. So, it already looks familiar in the sense that this is nothing but the summation over the Boltzmann factor for n new particles. Okay. So, I am going to call it as the canonical partition function with n new particles. If you recall, this is the canonical partition function for n new particles, because the only thing that is so the inner sum is at constant temperature at constant volume, okay, and now it is at a constant n nu. So, this is a partition function for n v t or the canonical partition function. N is not varying for the inner sum, it is constant. So, it is a partition function for the canonical ensemble. So, that restricted sum is nothing but the canonical partition function. Now, we can also so I am going to write this as so, my grand canonical partition function is this expression summation over all n e raised to beta mu n times the canonical partition function. Okay. So, I am going to call this as equation 1. Okay. And now, you can compute averages of various quantities in our system. So, you can compute for example, average number of particles in the system, because n is a fluctuating quantity to keep chemical potential constant. Like I said, for every fluctuating random variable, we are interested in its moments. So, the first moment to compute is its average. So, to compute average number of particles, which is like saying what is the expectation value of n. Okay. Now, this is simple, this is nothing but summation over all nu, okay, n nu e to the the probability distribution function, which is nothing but fine, which is like saying my PDF here is going to tell me what is the probability of finding a microstate with n nu particles and having momenta in position which is given by nu. So, you simply sample your n nu in that PDF and the result would be nothing but your average number of particles. So, when you do this sampling, what do you get? You have to do this sampling, and this would be nothing but n nu, and your PDF is nothing but e to the power minus beta h nu minus mu n nu over the grand canonical partition function. Fine. Now, you can pull out n nu by simply taking a derivative with respect to beta mu. Okay. So, you can write down that I will take a derivative with respect to beta mu of the grand canonical partition function, okay, and the denominator already has a grand canonical partition function. Okay. So, this is nothing but you can write it as 1 upon beta d by d mu of ln z, where z is nothing but the grand canonical partition function. So, it is have a function of mu v and t. Okay. So, this is the expression for average number of particles in your system. Okay. So, look at your partition function, which is nothing but the sum over all degrees of freedom, and the degrees of freedom here are not just the position momentas, but they are also the number of particles in a given microstate. So, this is the number of particles in the system, also called as the mean n. You can also compute fluctuations of n. So, these are nothing but the second cumulant of the random variable n, and that is nothing but you take the second moment minus the square of the first moment, and then it is very simple to see that it is nothing but you can already see that this is d over d beta mu. You have to pull out n 2 times. So, it is a second derivative of this your canonical grand canonical partition function over the grand canonical partition function minus square of the first derivative okay. So, if you see this will the terms in the bracketed term is nothing but mean n, and the first term is nothing but the mean of n square, okay. And you can write this as nothing but d over d beta mu of you can write it as 1 upon z d z over d beta mu. Is it okay? So, by chain rule it will expand to the previous equality, and if you pay attention to the fact the term in the parenthesis is nothing but logarithm of the derivative of the logarithm of z. So, this is nothing but d over d beta mu of I can write this as fine. Okay. So, but now this term has already been computed. Okay. So, this term has already been computed. So, this is over here. So, this is nothing but your n itself. Okay. So, this is d over d beta mu of n. Okay. So, now you can see that this thing scales as n, because beta mu is in intensive quantity, n scales as n. Okay. So, your variance scales as n. Okay. So, our variance scales as n, this is my variance, okay, or the second cumulant. That tells me that the standard deviation, which is square root of my variance, will scale as square root n, which is the standard deviation. Now, we can see that the ratio of standard deviation over mean which is basically a quantification of ensemble equivalence, diminishes in the limit of large n. So, the ratio of width over mean, which will always signify how sharp your distribution is in the thermodynamic limit. So, this will be square root n over n, which is nothing but 1 upon square root n, and that will diminish or go to 0 in the thermodynamic limit. So, this is called as the ensemble equivalence. That means, our grand canonical system in the limit of n going to infinity, suppose this is a large room or a hall or an auditorium which is in grand canonical ensemble, would have its number of particles fixed. So, it would actually be a system looking very similar to a canonical ensemble. Its number of particles are fixed, no longer fluctuating. Well, you can argue that there is a fluctuation, and as you increase the system size, the width also increases, okay, of the distribution. But I am going to ask, what is the proportion of your width to mean, and that proportion would be a diminishing value in the thermodynamic limit. So, essentially it has features of a microcanonical ensemble as n goes to infinity. Okay. So, it is equivalent, not equal to, it is equivalent to, that is why we are saying it is equivalent to micro canonical ensemble, the ensemble where n is fixed. In your ensemble the n is not fixed, but it is the relative width over mean is a diminishing value. So, essentially its features are like that of a microcanonical ensemble as n goes to infinity. Now, we can develop connections with thermodynamics as usual. In all ensembles we can develop connections with thermodynamics, and these connections are always established through the partition function. So, I am going to bring down my partition function, which is a very important derivation. So, let us export our grand canonical partition function downstairs and build a connection with thermodynamics. Okay. So, let us export it here. Fantastic. So, we now have our and just to remind you that this is the canonical partition function. Okay. Now, I need an approximation of this partition function, because again computing this summation over infinity is difficult. So, can I approximate it? Now, you can approximate using a technique called as saddle point approximation, since n is very large. So, this is an approximation technique that is discussed in our appendix. So, you can refer to it. Since n is very large, we can take a large number of particles in the system, okay. And the distribution is sharp. By sharp distribution I mean I have already shown that the ratio of width over mean has gone to 0 as n goes to infinity. This is the meaning of a sharp distribution. Okay. I can approximate the summation in the above expression. We can approximate this grand canonical partition function by largest summand. So, grand canonical partition function is already a sum over so many terms. Okay. If you look at the right hand side of the grand canonical partition function, it is a sum over so many terms. Okay. The idea here is to not take the entire sum. The idea here is to use the saddle point approximation. Okay. So, this is called as the saddle point approximation. So, the sum will now be replaced by the maximum of the summand. Okay. This technique has been discussed in detail in the appendix. So, you can now write down the partition function the grand canonical partition function approximated by the maximum summand. Okay. Now, it is not an exact equality, it is an approximation. So, the maximum summand here, the first term would be e to the power beta mu n star here n star is the value that maximizes the exponential, and I have to also take, see it is a product of two values. So, I have to take maxima of both of them. So, I am going to take the maxima of z itself, the canonical partition function also. Okay. So, I will say that the n star here maximizes the grand canonical partition function. Okay. So, it has to maximize both the exponent e raised to beta mu n and the canonical partition function z. And this is nothing but if you look at our derivations, the canonical partition function, if you recall, was already approximated, the maxima of this was e to the power minus beta into free energy, if you recall. Okay, where F is free energy of a system. Okay. So, here E star is the free energy that minimizes the E star is the energy that minimizes free energy, and hence we take that free energy here. Okay. And so, then you can write it as basically drop all the stars, because now they are all the thermodynamic variables. So, you have dropped all the subscript and you can write it as e to the power minus beta into the free energy minus mu n. So, now all the quantities are asterisk wise. So, we have dropped the asterisk symbol for convenience. Okay. because these quantities are thermodynamic in nature. So, n star here is a thermodynamic n that maximizes it, E star is also thermodynamic. So, I am going to drop these symbols for convenience. Okay, because otherwise I will have a star on each symbol inside. So, dropping a symbol star with the understanding that all energies and all number of particles are already in the thermodynamic limit. So, n here in the final expression is the thermodynamic n, E star is the thermodynamic E, F is the thermodynamic F, free energy, and so on. So, I can write down this final equality as e to the power minus beta, the thermodynamic free energy or the Helmholtz free energy. I am going to write it as Helmholtz free energy is nothing but the sum of internal energy minus temperature entropy work minus mu n. So, E minus Ts is F. Okay. So, now what we have is basically all these are approximations. So, now if you look at this is my grand canonical partition function, and it is basically e to the power minus beta into some energy scale E minus Ts minus mu n. So, we can label this as some equation number, let us label it as equation number 2. So, if we define it, it is in our hands to define this energy scale. So, I am going to define it this energy scale, okay, just for convenience sake, as some grand potential. Okay. So, this is the energy scale that will build connections with thermodynamics. Okay. So, I am going to define my energy scale in this Boltzmann factor as grand potential. So, I can write down my grand canonical potential as e to the power minus beta xi. Okay. And now you can see that the connections from thermodynamics can be established by simply taking a logarithm. So, my thermodynamic energy scale is xi. So, this will be nothing but minus 1 upon beta ln the grand canonical potential. Compare this with the connection that you established in the context of the Gibbs canonical ensemble. So, there the relevant energy potential was the Gibbs free energy. In the canonical ensemble, the relevant energy scale was the Helmholtz free energy, and here you have the grand potential that sets up that connection from the statistical mechanics to thermodynamics. So, this is the very important result. So, if you know how to compute the partition function for a system, then you can use this relationship to compute various thermodynamic quantities. What do I mean by that? Well, I mean that if you know partition function, then you can invoke appropriate derivatives of the partition function and compute the thermodynamic quantities. For instance, our energy scale here is for thermodynamic quantities. I am going to stop after this and take the example of an ideal gas in the next lecture, but just to sort of end the discussion, I want to explain what I just said. Okay, how do I invoke appropriate derivatives? So, look at this energy scale that is in front of you, the grand potential. So, this is E minus Ts minus mu n. Okay. So, you start with that okay, and take the incremental derivatives, okay, or the differentials on the thermodynamic law. So, what you have is the following expression. Okay, fine. Now, you can use the first law of thermodynamics and do something with dE minus ds TdS minus mu dN. So, I can write this as I can substitute for dE minus TdS minus mu dN as simply minus PdV. Because the first law allows me to write down the heat energy as that flows into the system as the rise in internal energy plus pressure volume work done by the system minus the chemical work. Okay, so, minus PdV will simply be what I have substituted for. So, then if I look at this expression in front of me, I can compute pressure, entropy and number of particles by invoking the appropriate derivatives of the grand potential. Okay. So, I can write down pressure as a negative derivative of the grand potential with respect to volume. Okay. So, let me write this again. I can write it as a negative derivative of the grand potential at constant chemical potential and temperature, and I can compute entropy as minus derivative of the grand potential at constant temperature with respect to temperature at constant volume and chemical potential, and finally I can compute number of particles by taking derivative with respect to chemical potential. Fine. So, you can compute. So, here look into this, your system is at constant mu v and t, and derivative with respect to these thermodynamic variables of the grand potential provides the connection with thermodynamics. So, I can compute the pressure of my system, entropy of my system, number of particles of my system using these appropriate derivatives. So, you can substitute for xi in these derivatives from this expression and compute all these quantities. So, if you have the knowledge of xi, you can compute all these derivatives and invoke and compute the thermodynamic quantity. So, in the next class we will take the example, I will take a working example in the class and take the ideal gas as one system and do this calculation and compute pressure, entropy and number of particles at equilibrium. So, we break here, and when we meet in the next class I am going to discuss the ideal gas under a grand canonical ensemble, and we will compute various thermodynamic quantities that we have just discussed in this lecture. Thank you.